Hello everyone, this is Dr. Bilal. In my last video, I have introduced you to the basic mechanism of radical polymerization. In addition to this, I discussed in detail all type of monomers that can be polymerized by radical polymerization and how electronic effects like resonance effect, inductive effect and hyperconjugation helps us to understand how a monomer stabilizes the radical in order to polymerize by radical polymerization. In this video, I will discuss the initiation step of free radical polymerization. This discussion is centered around initiator and their decomposition behavior. Let us begin with the definition of initiator. Initiators are compounds that decompose to generate free radicals, which then attack monomers, double bond, and start the chain growth reaction. The first requirement for an initiator is that it must be a source of free radical. In addition, the radical must be produced at an acceptable rate, at convenient temperatures, have the required solubility behavior, and transfer their activity to the monomer efficiently. Free radical initiation can occur through several ways, like application of heat, ultraviolet and visible radiations, and with the help of ionizing light and redox reagents. On the basis of the process by which initiators produced radical, they are classified into different classes. First type of monomers are called photoinitiators. Ultraviolet or visible light can break some bonds to produce radical. For example, in diphenyl ketone, a light of particular wavelength is absorbed by a diphenyl ketone and form two free radicals. Similarly, in case of dialkyl benzyl ketones, two radicals are generated by absorbance of UV visible radiations. The bond cleaving pattern has been shown in this equation. Advantage of such photochemical initiator is that initiation can occur at room temperature. When molecules are exposed to light of high energy and shorter wavelength or high frequency, electrons can be removed. Remember these two equations whenever you want to compare energy, frequency and wavelength. We can see from this equation that energy and frequency are directly proportional, whereas energy and wavelength has inverse relation. The initiation by ionizing radiation is largely employed in industry and experimentally include neutron, X-rays, photons and alpha and beta particles. Now let me show you the simplified mechanism of free radical formation. The mechanism has electron removal pathway, also called oxidative pathway. Remember, loss of electron is called oxidation, as this results in increase in oxidation number. Oxidation number of AB species in this equation is 0, but after loss of electron it is +1. In the first step, as a result of loss of electron, a cationic radical is produced that can convert to radical A and B, that can convert to radical A and B cation or B cationic radical. In the next step, cation B gain electron to produce B radical. In the reductive pathway, again just small reminder, the gain of electron is called reduction as this results in reduce in oxidation number of the species. As AB species after gaining electron acquire a -1 oxidation state from 0. In the first step, after gain of electron, an anionic radical AB is formed that break down to A radical and B anion. In the next step, B anion is converted to B radical after loss of electron. Ionizing radiation-induced polymerization are generally carried out at room temperature. For such type of initiation, The reactions are so selected that the generated radicals are more stable than cations and anions. Let us talk about initiators that produce radical as a result of oxidation reduction reactions. These are called redox initiators. The redox is a combined term used for oxidation reduction reactions. Peroxide in combination with reducing agents are a common source of radicals. For example, the reaction of hydrogen peroxide with ferrous ion. Ferrous ion also promotes the decomposition of variety of other compounds including various types of organic peroxides. An example of organic peroxide is cumene hydroperoxide that combine with ferrous ion that on homolytic cleavage of oxygen-oxygen bond to produce cumyloxyl radical. Other reducing agent, chromium ion, vanadium, titanium, cobalt and copper ions can be employed in place of ferrous ion. Another redox system is based on inorganic reductant and inorganic oxidants. In this reaction, iron 2 in its plus 2 oxidation state known as Fe plus 2 or ferrous ion, this iron ion acts as a reductant, meaning it donates electron. When it gives up an electron, Fe plus 2 becomes Fe plus 3. The process is called oxidation and oxidation state of iron increased from plus 2 to plus 3. On the other side, we have an oxidizing agent, which is a substance that accepts those electrons. As it takes in the electrons from iron, it undergoes reduction. In short, we can say reducing agent causes oxidation and oxidizing agent causes reduction. The sum of both these reactions is redox. The prime advantage of redox initiation is that radical production occurs at reasonable rates over a wide range of temperatures. Let us talk about the thermal initiation of radical polymerization. First type of compounds that fall in this class are peroxo compounds. This is a group of initiators that include both organic and inorganic types. Each decomposes at different temperatures. Here is a breakdown. Benzoyl peroxide decomposes between 40 degrees Celsius and 100 degrees Celsius. When the reaction is carried out in bulk, it means in solventless condition, the benzoyl radical generated by decomposition of benzoyl peroxide directly react and start polymerization. However, in case of polymerization reaction carried out in solvent, the benzoyl radical is not stable and converted to phenyl radical by emission of carbon dioxide. Hydrogen peroxide decomposes between 30 and 80 degrees Celsius, produces hydroxyl radicals, which are short-lived but powerful initiators. Cumyl hydroperoxide decomposes between 50 and 120 degrees Celsius. It generates cumyloxy radicals. Ditertiary butyl peroxide requires higher temperature between 80 and 150 degrees Celsius. It produces tertiary butyloxy radicals, which are more stable and useful in high temperature polymerizations. Let us take an example of inorganic peroxides such as potassium peroxodisulfate. This is an inorganic peroxide. It decomposes in the range of 40 and 100 degrees Celsius. Upon decomposition, it generates sulfate radicals, which are effective at attacking monomer to start the polymer chain. Let's turn our attention to azo compounds, which are among the most widely used thermal radical initiator. What makes them so useful is their nitrogen-nitrogen bridge. When these azo compounds are heated, the azo bond homolytically cleaves, releasing nitrogen gas and generating two carbon-centered radicals that can kick off a free radical chain reaction. First example of these azo compound 2,2-azo-bis isobutyl nitrile or AIBN. Between 50 and 70 degrees Celsius, the nitrogen-nitrogen bond breaks to give two radicals plus nitrogen gas. The clean evolution of nitrogen makes AIBN especially attractive for solution and bulk polymerization. The next example is 2,2-azobis 2-amidino-propane. It decomposes at slightly lower windows between 40 and 60 degrees Celsius to yield amidino-propyl radical and nitrogen. Because it's water soluble, it's ideal for emulsion or suspension polymerization. Finally, 2,2-azobis 4-cyanopentanoic acid carries carboxylic acid end group. It decomposes from 40 to 70 degrees Celsius, producing radicals and nitrogen. We know that initiator decomposed to produce two radicals. In principle, all the radicals should start the chain. If F represents the efficiency of initiator, which is defined as ratio of radicals incorporated to polymer to the radical formed by initiator. In case all the radicals generated are incorporated to polymer chain, the value of F will be equal to 1. But actually, value of F is always less than 1. Usually, its value is between 0.3 and 0.8. And for any reaction, value of F can be determined experimentally. The value of F less than 1 means all the radicals generated are not incorporated to polymer. It is considered that the initiators and formed radicals are trapped into cage of solvent. This means the radical must have to diffuse out of the solvent cage in order to react. More they stay longer in the cage, more they can undergo side reactions and cannot initiate the polymer chain. This reduced efficiency of initiator due to solvent cage is termed as cage effect. Let us understand graphically how cage effect works. Consider an initiator is surrounded by solvent molecules. The initiator is decomposed to produce two radicals inside cage. One possibility is that both the radical becomes two stable molecules after donation of proton to other molecule. As a result of this, no initiation happen. Second possibility is that both the radical recombine to produce stable molecule that cannot initiate polymerization. Two radicals produced by decomposition of AIBN, for example, the two radicals produced by decomposition of AIBN initiator can recombine in two ways to produce stable molecules that cannot initiate polymerization. Another possibility is that the initiator diffuse out of the solvent cage and react with already growing polymer chain and terminate that chain with process known as chain transfer by initiator. As a result, only one radical is left that can react with monomer to initiate polymerization. Let us understand complete mechanism of initiator efficiency and cage effect and see what reactions are responsible for lowering the value of F, which is called cage effect. In the first step, the initiator is decomposed to produce radicals. The bracket indicates the presence of solvent cage. One possibility is that they combine again to form neutral molecules within the solvent cage that cannot initiate polymer chain. Other possibility is that one of the radical is converted to phenyl radical. These species can diffuse out of the cage and can initiate polymer chain. The other possibility is that they recombine to become neutral molecules. The other possible reaction of benzoyl oxy radical is that both benzoyl oxy radical diffused out of cage to form two phenyl radical that can initiate the polymer chain. The other possibility is recombination within solvent cage. Now consider again benzoyl oxy radical. It can react with monomer to start polymer chain. Yet another possibility is that the benzoyl oxy radical diffuse out of the solvent cage. This benzoyl oxy radical can further decompose to phenyl radical by the release of carbon dioxide. The other possibility is that the benzyl oxy radical react with monomer to initiate polymerization. There are further three reaction possibilities for phenyl radical. It can recombine with benzyl oxy radical to form a neutral molecule, or it can react with phenyl radical to form neutral molecule, or it can react with monomer to start the polymer chain. From this mechanism, we see some products contain active radical that can initiate polymerization as highlighted in green. However, some products are stable molecules that cannot initiate polymerization and are responsible for lowering initiator efficiency. These are highlighted in red. Loading of F by these side reaction is referred to as the cage effect. The phenomenon is observed in almost all initiation systems produce radical pair. However, there are some initiation systems that produce only one radical. They do not show cage effect. Let us understand the concept of self-initiating polymerization. For this, let us specifically look at the thermal polymerization of styrene. In this process, the monomer styrene can actually kickstart polymerization without the need of an external initiator. Now, two major mechanisms has been proposed to explain how this happens, one by Mayo and other by Fleury. Let us start with Mayo's model. Here two styrene molecules react and form a dimer which we will call AH. This dimer can break apart into two mono radicals, A' and HM'. These radicals go on to initiate polymer chain through mono radical polymerization. Fleury's approach is quite similar but uses slightly different terminology. He suggests that two styrene molecules form a dimer labeled M2, which then dissociate into two mono radicals that trigger polymer formation. Both mechanisms suggest styrene has a built-in capacity to begin its own polymerization. The self-polymerization of monomer is not desired, as with self-initiation we cannot achieve polymer of desired properties. This leads us to a key question: how can we prevent self-initiating polymerization? That's what we will explore next. For further reading, these are very nice books containing very nice explanation of the radical polymerization. If you still have question, then please write in the comment section. Thanks for watching.